Okay, welcome back to Real Analysis. We are nearly wrapping up our work in Chapter 2 on sequences. In this second to the last section, we're going to cover in Chapter 2, Section 2.10, going to introduce a technical tool called Subsequences. So we'll give some results about how we use this technical tool. It'll be used quite heavily in the remainder of the material of our course. It's a very powerful way to establish some of the material results I want to show you. So we're going to give an introduction, a definition of subsequences, play around with some examples, look at some results, and then accumulate with a result called the Bolzano-Weierstrass theorem. Okay, so we'll get going here. What is a subsequence? You know, colloquially, a subsequence just consists of some of the terms of a given sequence. But to be a little bit more precise by that, if somebody gives me a sequence, so the author here is writing it out, S1, S2, and so on, then by a subsequence of it, I mean some of the terms in the sense, so I'm going to use a double index here, Sn sub 1, Sn sub 2, and so on, where that sequence N1, N2, and N3 is an increasing sequence of natural numbers. All right, so this is kind of a technical way of saying that from the terms in the sequence Sn, I'm selecting some of them. Maybe S2 is the first one. So N sub 1 might be a 2. And then the next one might be S5. So N sub 2 would be a 5, and so on. So these N sub i's are the indices in the original sequence. And so they form an increasing sequence of them, and it has no end. So this is a technical way of saying that we're taking some of the terms of the sequence. So it's a subsequence. Okay, so that's the definition and the notation we're going to use. Let's kind of play around with a couple of results here. If you give me a sequence, this is not a theorem in your book, so I'm just going to call it theorem. It doesn't have a number. But what am I saying? If you take a sequence Sn, and then you take any subsequence of it. So this is our notation I'm going to use, S sub n sub k. So you know that sequence of terms, n sub 1, n sub 2, and so on, is strictly increasing. Then the theorem is, well, if the sequence converges to L, then so does S sub n sub k. So said another way, every subsequence of a convergent sequence converges, and it has the same limit. Okay, that's kind of a colloquial way of saying what this theorem says. Every sequence of a convergent sequence converges and has the same limit. Cool. Okay, so how to prove that? Well, by definition of subsequence, the n sub k's are a strictly increasing sequence of natural numbers. Certainly, n sub 1 is at least 1. The first term in the subsequence is at the very least the first term in the sequence. And for that matter, for every k, the n-kth term, n sub k, has to be at least k, right? So you might want to stop the video and think about that for a second. But what I'm saying is if you select a subset of the indices, and not just any subset, but an infinite increasing subset of the natural numbers, well, the kth element that you pick, because it's strictly increasing, has to be at least k. So n sub 1 is at least 1, and n sub 2 is at least 2, and so on. All right, so I'm going to kind of let you think through the details of that, but I'm just going to go ahead and use it here. So I want to show my subsequence converges, so I start by picking an epsilon. And then since my sequence converges to L, that means there's some value, capital N, so that when little n exceeds that, the difference of the sequence terms is less than L. Okay, so now if I take k bigger than that same n, well, what we just said is that the subsequence term n sub k has to be at least k, which is bigger than n. So the corresponding subsequence term, s sub n sub k, it differs from L by less than epsilon as well, right? Because n sub k is bigger than the threshold. So by definition, the subsequence converges to L as k goes to infinity. Nice. Another kind of quick remark here, if I unwind the definition of what it means to not converge, we've talked about this before. If a sequence Sn doesn't converge to L, it means there exists some positive number epsilon, so that for every value you pick in the natural numbers, I'm going to call it k, kind of matching my subsequence notation. So there exists an epsilon such that for every k, I can find some index, which I'm calling n sub k, because it depends on this k, that would be bigger than or equal to k, and the difference between it and L would be at least epsilon. Okay, so that's just the negation of our definition of converging. Okay, so since we can do that for every k, we can do it for k equal 1 and k equal 2 and k equal 3 and so on. So we get an n sub 1 and n sub 2 and so on. Those things are going to form a strictly increasing sequence. So it exactly gives rise to a subsequence, S sub n sub k of our original sequence Sn, and all of the subsequence terms differ from L by at least epsilon. All right. So it's kind of a useful, this is going to be a technical tool in the future. I'm just making it as a remark here, but if a sequence doesn't converge to L, then you can find a subsequence of it that's quote unquote bounded away from L by some distance. There's some subsequence, the terms never get within some positive number epsilon of L. Cool. A second remark, which I'm kind of giving a little bit more precise name, called a divergence criteria. If you have a sequence and it has two convergent subsequences, let's call them Sn sub k and Sm sub k, and they're convergent, so they have limits, but the limits aren't the same, well, then the sequence can't converge. The original sequence S sub n can't converge, right? Because we proved above in our theorem, this is just kind of a corollary of it. We said that if a sequence converges, then all of its subsequences converge to the same limit. So if you have two subsequences that converge to different limits, well, then your original sequence can't converge. So just as a real quick example of that, you guys proved, I think, in a homework problem, or maybe we did it in lecture, that the sequence -1 to the n diverges. And you did it epsilonically. Well, you could do it with this divergence criteria. If you look at only the even terms of that sequence, they're all equal to 1, so it converges to 1. If you look only at the odd terms, they're all equal to -1, so they converge to -1. 1 and -1 aren't the same number, so I've got two subsequences. They converge, but the limits aren't equal, so the sequence diverges. It's kind of a handy tool to have around. Sometimes if you're trying to show a sequence diverges and you don't want to do it epsilonically, if you can just kind of strategically pick a couple of subsequences, each of which converge and the limits aren't the same, then there you go. Nice. So again, that's not written, at least in the section of your book, although the word divergence should definitely have an E in it. Let me try to fix that before we move on. Okay. Back to a book result here. This is kind of the main, it's almost like a lemma to this Bolzano-Weierstrass theorem I want to prove at the end of the lecture, but it's important enough to be called a theorem in and of itself. Right? It's kind of a technical, all of the material, all of the results in this section are technical, but you want to try to kind of wrap your head around them because they're going to become kind of everyday tools for us in our future work. So this is crucial stuff. So what's the theorem say? It says that every sequence has a monotonic subsequence. So from any sequence in the world, I can always select a subsequence that's monotonic. I don't know what flavor. Maybe it's non-decreasing, maybe it's non-increasing, maybe it's increasing, maybe it's decreasing, but it's got to have one. Okay, and this is fairly intuitive that that's true, but let's try to give the proof. So give me any sequence. It's a theorem about any sequence. That can be a little intimidating. And then I'm going to introduce a technical device. I'm going to call a term of it, S sub n. I'm going to call it a peak. Your book uses the three-word phrase turn back point. It's okay, but I don't really like it. I prefer peak. So what makes a term a peak? A term is a peak if every single term that's after it in the sequence is less than or equal to it. Okay, so I'm going to ruin the notes here by drawing a little picture. So imagine here's maybe my M, and this dot's Y value represents the sequence term S sub M. So S sub M is a peak if every single term after it never has a sequence value that exceeds the sequence value at S sub M. So all subsequent terms are going to be, their Y values, if you're thinking of it as a plot, are going to be less than or equal to that S sub M. They might equal it, but they can't ever be bigger than it. Okay. So that's why it's kind of called a peak. You can kind of think of the sequence falls after it. So if you're a hiker, you might also think of you've reached the peak when the rest of your hike is not going to go up. There's no more hill climbing. Okay, so that's what I mean by a peak. And I'm just going to consider two cases. Perhaps, I don't know if it's the case, but it might be that my given sequence has infinitely many of these peaks. Okay, so let's name them. SM1, SM2, SM3, where these numbers, M1 is strictly less than M2, and so on. So I'm just kind of ordering the infinitely many peaks in increasing order of the indices. Okay, first peak, second peak, third peak, and there's infinitely many of them. All right, so each one of these things, each one of these SMKs is a peak. So it means that the subsequent terms in particular, like SM1 is a peak. Well, M2 comes later in the sequence. So by the definition of peak, SM2 is less than or equal to it. SM3 would be less than or equal to that, and so on, right? Because these indices, M1, M2, they're getting strictly bigger. So this sequence, this subsequence is what? It's just the set of those peaks. And it's non-increasing subsequence by definition. So there's my monotonic subsequence. In this case, if I have infinitely many peaks, my monotonic subsequence happens to be non-increasing. All right, cool. But it's not necessarily the case that I have infinitely many peaks. So what's the kind of opposite of that? The other case, there's just finitely many peaks. That's the only other case I have to consider. Given a sequence, it either has infinitely many peaks or it doesn't. Okay, so if it has finitely many peaks, then let's list them. Let's say that SM1, SM2, where again, I have in mind here that I'll write it, M1 is strictly less than M2, strictly less than, so up to this biggest one, M sub P. SMP is the last quote unquote peak, last in the sense that its index, M sub P, is the biggest. Okay, so any index past M sub P, what do I know? You're not a peak. That's the crucial part. Stop the video. I'm going to say that one more time and then stop the video. If I take an index that's strictly bigger than M sub P, then S sub that index cannot be a peak because this is the complete list of them. Okay, so in particular, if I look at the number that's, say, one more than M sub P, I'm going to suggestively call that number N sub 1. That term, Sn sub 1, cannot be a peak. It can't be because it's past the last peak in my sequence. Okay, if you're not a peak, I'm just negating the definition of it. There must be some index that's bigger than your index, and that sequence term is bigger, right? If you're not a peak, there's something after you in the sequence that's bigger than you. Call it SN2. Okay, but N2 is bigger than N1, which is bigger than MP, so it's not a peak either. So play the game again. There has to be some index bigger than N2 whose sequence term is bigger. SM2 is not a peak. Something after it has to be bigger. Continuing this process, we will generate this subsequence, SN1, SM2. It's strictly increasing. It's or by our terminology, pardon me, it's increasing subsequence, right? It's an increasing subsequence. There's no N in the end of the word hence. Cool. So just summarizing in case one, if you have infinitely many peaks, okay, take the subsequence of them, it's monotonic. It's non-increasing. If there's only finitely many peaks, then you can find a subsequence that's increasing. It's monotonic. So in any way you slice it, this sequence Sn had a monotonic subsequence. Okay, so that brings us to the final result of the lecture. It's a famous theorem, the Bolzano-Weierstrass theorem. Okay, Bolzano and Virusdrost, two mathematicians. Your book says this. I believe Bolzano was a Czech mathematician. Virusdrost, I believe, was a German mathematician, but you can check your text to make sure that I'm not wrong. All right, you can, if I'm wrong, you can flame me in the comments on this public YouTube video. So what does the Bolzano-Weierstrass theorem say? It says that every bounded sequence contains a convergent subsequence. This will be an important tool for us as we move through some of the later material in the course. Okay, the proof of it is pretty short because most of the work was done in the previous theorem where we showed that every sequence has a monotonic sequence. Right, we're just going to kind of couple this with the monotone convergence theorem. So let's check it out. So let's take a sequence called Sn and suppose it's bounded. All right, so the theorem that we just proved, 239, says that it has some monotonic subsequence. We don't care which flavor. If it's non-decreasing, non-increasing, increasing, decreasing, we don't care. It has to have a monotonic subsequence. And I'm going to let you kind of think through the details, but that subsequence would also be bounded. All right, so that's why I'm putting my little question here, but I want you to stop the video and answer that question technically in the technical definition sense of bounded. So I start with a bounded sequence. Theorem 2.39 says it's got to have a monotonic subsequence, which is also bounded. But then we apply the monotone convergence theorem to that subsequence. That subsequence has to converge. It's a bounded monotonic sequence. So there you go. This bounded sequence has a convergent subsequence. That's it. That's the short proof of the Bolzano-Weierstrass theorem. Okay, so we're going to end the video right there. Thanks for listening.